Hello and welcome to another lecture on differentiability. Today we shall be discussing about derivatives of inverse trigonometric functions. Later we are going to discuss derivatives of a composite function, and finally we shall conclude this lecture on differentiability by discussing some numerical problems that would be based on finding the differentiation of inverse trigonometric functions and composite functions. So now starting with the derivatives of inverse trigonometric functions. Now we have already discussed in one of the chapters about inverse trigonometric functions. In this chapter, we are going to discuss the derivatives of the given inverse trigonometric functions. The derivative of sine inverse x is denoted as d by dx of sine inverse x, which is read as derivative of sine inverse x with respect to x, and this is equal to 1 divided by root of 1 minus x square, where x square is less than equal to 1, which implies that x belong to interval minus 1 to 1. Next we are going to find the derivative of cos inverse x. Its derivative is denoted as d by dx of cos inverse x, which is equal to minus of 1 by root of 1 minus x square for x belonging to interval minus 1 to 1. Next we have the derivative of tan inverse x for all x belonging to R. Now here the differentiation of tan inverse x is denoted as d by dx of tan inverse x, and its value is equal to 1 divided by 1 plus x square for x belonging to R. Next we have the derivative of cot inverse x, which is denoted as d by dx of cot inverse x and is equal to minus 1 divided by 1 plus x square for x belonging to R. Next we have the derivative of sec inverse x, where x belongs to R minus interval minus 1 to 1. The derivative of sec inverse x is denoted as d by dx of sec inverse x and is equal to 1 divided by mod of x into root of x square minus 1, where x square is less than 1, which implies that x belongs to R into minus 1 to 1. Next we are going to find the derivative of cosec inverse x, where x belongs to R minus interval of minus 1 to 1. The derivative of cosec inverse x is denoted as d by dx of cosec inverse x, and its value is equal to minus 1 divided by mod of x into root of x square minus 1, where x square is less than 1, which implies that x belongs to R into interval of minus 1 to 1. Thus we have evaluated or discussed the values of the derivatives of the inverse trigonometric functions. Now let's discuss the derivatives of a composite function. Before discussing the differentiation of a composite function, let us first discuss the definition of a composite function. If a function f maps x onto u and a function g maps u onto y, then the function for each x maps x onto y and is denoted by gf or gof and is called the composite function of g on f. For example, if f, which is a function of x, is equal to 5x square plus 3x plus 7, which is equal to u, and another function g, which is a function of u, is equal to u4, and g in terms of fx is written as 5x square plus 3x plus 7 whole to power 4, which is thus equal to u4. Or y be the composite function of g on f, which is denoted as gf, is equal to u to power 4 and u is equal to 5x square plus 3x plus 7, and the dy by dx is equal to dy by du into du by dx. For differentiation of a composite function, if fx and gx are differentiable functions, then fog, that is composite function of g on f, is also differentiable, and derivative of function fog with respect to x is equal to f gx into derivative of gx. Or we can write d by dx of fog, which is a function of x, is equal to d by dg into fog, which is a function of x, into d by dx of gx. Now if y is a function of u and u is a function of x, then dy by dx is equal to dy by du into du by dx. That is, derivative of y with respect to x is equal to derivative of y with respect to u into derivative of u with respect to x. Next we have the extension of a function of a function. For that, if y is equal to function of u and u is a function of v and v is a function of g, which is a function of x, then dy by dx is equal to dy by du into du by dv into dv by dx. That is, derivative of y with respect to x is equal to derivative of y with respect to u into derivative of u with respect to v into derivative of v with respect to x. This is also known as the chain rule, which is very useful in differentiation. Next we are going to consider the problem. Now here we are required to differentiate the following function with respect to x, which is equal to 1 divided by a square minus x cube to power 3 by 2. Now here let us suppose y equal to 1 by a square minus x cube to power 3 by 2 and u is equal to a square minus x cube, which means y is equal to u to power minus 3 by 2, where u is equal to a square minus x cube. Therefore, dy by dx is equal to minus 3 by 2 u of minus 5 by 2, and du by dx is equal to minus 3x square. Now as we have discussed in this lecture that dy by dx would be equal to dy by du into du by dx. Now we substitute the values of dy by dx and du by dx as specified in equation number 1 in the value of dy by dx, which gives us dy by dx as minus 3 by 2 u to power minus 5 by 2 into minus of 3x square. This can be further simplified and rewritten as 9 by 2 u to power minus 5 by 2 into x square. Next we are going to substitute the values of u in this equation, which is, let's say, label as equation number 2, which is obtained as 9 by 2 a square minus x cube whole to power minus 5 by 2 into x. Now this can be further simplified and written as 9x square divided by 2 u to power 5 by 2, which is equal to a square minus x cube to power 5 by 2. With this we conclude this lecture on differentiation, which was based on inverse trigonometric functions and composite functions.